Hello and welcome back. In this video I want to start discussing how we can analyze nanoindentation data with machine learning. Nanoindentation is a contemporary method in material science, how we can use to characterize materials on the nanoscale. The technique involves using the controlled application of force throughout a sharp tip, typically on the nanometer scale radius, with subsequent measurements of the material response. So we observe the depth of the penetration of the tip into the material, and then nanoindentation provides us valuable data on hardness, elastic modulus, and other mechanical parameters. The application of this method can be found across a wide spectrum of materials, including metals, ceramics, polymers, even biological tissues. This method is instrumental in gaining insights into the nuanced mechanical behavior of materials and aids researchers and engineers in the precise tailoring of materials for enhanced performance and durability across different applications. So what we want to do here is we have a commercial dual-phase steel sample that we want to analyze, a dual-phase DP800 steel, and if we put this into an electron microscope after preparing the sample suitably, it may look like this. We immediately notice that there are some artifacts that we need to take care of. So this is what we need to keep in mind for our later analysis. Now we place an array of nanoindentations on the sample and record the response from the nanoindenter. If we look at this again at a 5 kV acceleration voltage, we notice the following picture. So you can see here all the nanoindentation overlaid on the structure of the material. We already see here our artifacts that we have discovered before. If we now increase our acceleration voltage to 20 kV, the electron beam penetrates deeper into the material. We still see the grid of the nanoindentation all across our material sample that we want to analyze, plus a lot more of these artifacts are now apparent. So let's start analyzing the data. We use pandas and a range of other methods, so let's start by loading the data into a pandas data frame. We've conveniently put this into a file called nanoindentation CSV. So once we load the data, we see that we have the X and Y position of the data that we record. So these X and Y's correspond to all the indents that we can see in the electron microscope image here. And then what is recorded by the machine: load, depth, stiffness, modulus, and hardness. In the first step, we look at the hardness. Because we have two phase in this dual phase steel, hence the name, we expect two different values for the hardness. And if we plot this into a histogram, this is exactly what we do see. There is a peak here and a peak here. We can do the same for the elastic modulus, and we see that this is more or less a Gaussian distribution with some tails more on the left side than on the right side. Next, we look at the distribution of the measured hardness and elastic modulus across the sample. To do this, we can create a scatter plot of the X and Y position of the measurements, and then use the value for either the hardness or the elastic modulus as a choice of color. Using a suitable color map from black to red, we can see how the different areas correspond to measured hardnesses. So here's all the Python code to create such a plot. We use Seaborn and a scatter plot. We have the X values and the Y values, and the color is given by the hardness. And here we have some of the code that creates our color bar. And on the right, we do this for the same thing for the elastic modulus, so the only difference here is that we use the modulus instead of the hardness, and the same for the legend. And if we do that, we can see that the plot looks similar to the electron microscope image, just with the hardness values, and each of these dots now corresponds to one nanoindentation, and the color corresponds to the hardness on the left and the elastic modulus on the right. We can see that there are distinct phases. Here are these bands that we have already seen in the electron microscope image, plus some of the artifacts are already quite apparent, and the elastic modulus and the hardness show this in a different way. You can also plot this as a heat map instead of a scatter plot. It's the same functionality, but you can see that the plots are visually a bit more peeling, and for technical reasons they are rotated by 90 degrees because the heat map and the scatter plot do this in their implementation. It's also useful to define the quantity m modulus squared by hardness. This is more an empirical parameter that can be used to highlight the difference between the two phases, and we add this as a data frame. So we have a new value, data frame m2h is the modulus times the modulus divided by the hardness. So this is just added, and we can plot this value again. And we also notice there are some more artifacts now visible in this kind of plot, where here along this line there was evidently some issue with the nanoindentation in this array. Our original task was to segment the two phases. We have a dual phase steel, so we want to differentiate between the martensite and the ferrite phase. Let's start with the simplest approach. The simplest thing we can do is place a cut on a specific value of the hardness to discriminate between the two phases. If we go back to our plot here of the hardness, we can see that there's one distinct peak here and one distinct peak here. So if we place a cut somewhere here in the middle, we expect that we can discriminate between those two phases. So let's do that. And say everything greater than 5. If we do that, we can see we can indeed isolate this phase with the artifacts, but because we only have now one cut, the artifacts now go to the other phase. We can now discriminate between this phase and everything that is white. We only have two phases now, greater than 5 and smaller or equal than 5, and we have two hardness clusters with these standard deviations.